Welcome back to The Explainer. I am so thrilled you're joining in today because honestly, we are going on a totally fascinating journey. We're going to crack open one of the most talked about yet kind of least understood technologies of our time, and that is the neural network. We're going to start at the absolute microscopic level, right down to single artificial neurons, and then scale all the way up to see how a fully trained network actually visualizes the world around it. It is an incredibly cool process, and we're going to make the whole thing crystal clear.
But first, let's just start with a massive question. What does an AI actually see? I mean, for a long time, these networks were treated as a total black box. We feed data in, we get a prediction out, and that entire middle part is just a giant mysterious soup of numbers. But what if we could look inside? What if we could actually generate an image that shows us exactly what a neural network is looking for when it tries to identify a dog, or a car, or even a cloud? Well, today we are going to unlock that black box.
So, here is our roadmap for the explainer today. 1. Anatomy of a neural network. 2. Weights, biases, and activations. 3. Learning through gradient descent. 4. Visualizing what networks see. 5. The enemy, high-frequency noise. And 6. Taming the network.
Section 1. Anatomy of a neural network.
Okay, so to understand the massive, highly complex behaviors of AI, we really have to start small, very small. We need to look at the computational graph itself, and the absolute foundation of it all is the artificial neuron. It's very loosely based on how we think the human brain works, but an artificial neuron is really just a simple computational element. It receives inputs, performs a mathematical operation on them, and then passes the result forward. By chaining millions of these software neurons together into hidden layers, they send messages to one another, essentially building up a complex network that is capable of learning incredibly intricate patterns.
Section 2. Weights, biases, and activations.
Right, so if neurons are the structure, weights and biases are the dials the network turns to actually learn anything. First up, we have weights. You can kind of think of a weight as the thickness of the connection between two neurons. It's a numerical value that determines just how much influence a specific input has on the final output. If a feature is, say, really important for making a prediction, the network is going to assign it a heavy, thick connection during training. But if it's irrelevant, that weight just shrinks right down.
Next up, we have biases. Now, while weights multiply the input, biases are simply added on top. They shift the output of a neuron, giving the model some much-needed flexibility. Think of a bias as a base level, right, or a starting point. It allows a neuron to activate and fire off a signal even when the raw inputs coming into it are super low. It basically gives the network independence from just relying on the raw input data.
So, the really crucial point here is what happens after the weights and biases are calculated. The result gets passed through an activation function, and we've got a few options here. Sigmoid squashes numbers between 0 and 1. Tan squashes them between -1 and +1. Both are great, but they can suffer from this annoying issue called vanishing gradients, where the learning just slows to a complete crawl. Then there's Relio, which is incredibly popular and super efficient because it simply keeps positive numbers and zeroes out the negatives. Though watch out, it can sometimes lead to dead neurons that just never fire. But the major, absolutely critical takeaway here is that these functions must be nonlinear. Because without nonlinearity, no matter how many layers you stack up, your network is basically just one giant flat line that's completely incapable of learning anything complex.
Section 3. Learning through gradient descent.
Well, we know the parts now, but how does the network actually improve its predictions over time? I mean, how does it correct its own mistakes? The answer is gradient descent. I want you to imagine a vast, hilly landscape. The height of those hills represents the network's error, basically how wrong its predictions are. The whole goal of the network is to find the lowest possible valley, the absolute minimum of error. Gradient descent is the mathematical compass that points the network down the steepest slope. It calculates the negative gradient of the function and iteratively takes tiny steps downwards. And the size of those steps? That's controlled by a setting we call the learning rate.
Let's break down how this actually builds into a continuous loop. The first 4 steps represent the forward pass. Data goes into the input layer, we calculate that weighted sum, add our bias, and pass it through the activation function to get our prediction. Pretty straightforward, but then comes the magic. Step 5 is error calculation. We compare our prediction to the real, true answer. Finally, in step 6, we use backpropagation. The network sends that error backward, tweaking every single weight and bias slightly, using the chain rule from calculus, so the very next time, the error is just a little bit smaller.
But wait, how do we escape a local minimum? Remember that mountainous landscape we just talked about?
Sometimes the network steps down into a small, shallow valley, a local minimum, and thinks, great, I'm finished, completely missing the massive, deep canyon of the global minimum right nearby. It might also just get stuck on flat plateaus, where the error doesn't even seem to change at all. So, to fix this, we use clever techniques like momentum, which basically gives our algorithm enough speed to roll up and out of a shallow valley. Or we dynamically tweak our learning rates to take larger steps right over those flat plateaus.
Section 4. Visualizing what networks see.
Okay, let's zoom out a bit to the macro level. Feature visualization completely flips the script on everything we just talked about. Normally, we optimize the weights to give us a better prediction for a fixed, real image. But what if we freeze the weights, start with an image of pure, random TV static, and optimize the image itself? We use those exact same derivatives, but we tweak the input pixels until they cause a specific neuron to fire as intensely as possible. By doing this, we are literally watching the network hallucinate exactly what it is looking for.
And you know, when researchers at Distill did this with a network called GoogleNet, they found this staggeringly beautiful hierarchy. If we map out this progression, in layer 1, the network is really just looking for basic edges and lines. By layer 2, those edges combine into textures. Layer 3 turns those textures into complex geometric patterns. By layer 4, the network is assembling actual parts. Think the eyes or snouts of an animal. And finally, in layer 5, the network is activating in response to full objects, like complete animal faces or buildings. It literally builds understanding piece by piece.
Section 5. The enemy. High-frequency noise.
But of course, there is a plot twist. If you just let this optimization run wild, you don't actually get beautiful animal faces. The unregularized noise just ends up looking like complete garbage. It's a nonsensical, high-frequency optical illusion. But the crazy part? The neural network looks at this static and confidently declares, yes, absolutely, that is a dog. It's cheating, basically. It's finding ways to activate its neurons using bizarre mathematical patterns that never actually exist in the real world. We call these adversarial examples. If we want to understand what the model actually cares about in real life, to get realistic, recognizable examples, we have to constrain this process.
A major culprit behind all this noise actually comes from the very architecture of the network itself, specifically efficiency tricks like strided convolutions and max pooling. Max pooling is an operation used to downsample an image. It uses a sliding window across the data, defined by a kernel size and how far it steps across the image, which we call the stride length, and it literally only keeps the maximum value in that window. Now, its main purpose is great. It boosts computational efficiency and helps avoid overfitting by summarizing features. But here's the catch. Scanning images this way leaves behind these harsh, high-frequency checkerboard artifacts in the gradient. So when we backpropagate through these pooling operations over and over again, it just amplifies that static, completely destroying our beautiful visual hallucinations.
Section 6. Taming the network.
So how on earth do we fix it? We have to force the network to produce coherent, human-readable images. And researchers have developed a whole toolbox of regularization techniques to do just that. They use frequency penalization, which means literally blurring the image slightly during optimization to kill off that high-frequency noise. They use transformation robustness. They'll randomly jitter, scale, and rotate the image during the process, forcing the network to focus on robust real features rather than fragile static. They even use learned priors from other generative models to enforce realistic rules and diversity terms to force the network to show us different facets of an object. Like showing both the soccer ball and the tennis ball rather than just inventing one weird generic sphere.
But actually, one of the most powerful tricks in this entire toolbox is preconditioning. Instead of optimizing the raw pixels directly, researchers realized they could optimize the image in a Fourier transform space where colors are decorrelated. I know that sounds like a mouthful, but basically, by changing the mathematical space where the gradient descent happens, they stretch and shrink the landscape itself, making the descent radically easier for the algorithm. And the resulting visualizations? They develop much faster and look far more photorealistic. Which brings us to this incredibly poignant quote from the Distill researchers. Feature visualization stands out as one of the most promising and developed research directions. Combined with additional tools, it will empower humans to understand these systems. Opening this black box is absolutely critical, as these models make decisions that impact our daily lives, from healthcare diagnostics to autonomous driving. We absolutely must be able to audit them and understand exactly what features they are using to make their choices.
So I want to leave you with this one thought. If neural networks can hallucinate optical illusions to trick their own optimization process, what other hidden facets, strange correlations, and bizarre representations are lurking deep inside their activation space? We are really just beginning to map the mind of the machine. Thank you so much for joining me on this explainer. Keep wondering,
Keep learning, and I will catch you in the next one.